Okay. Welcome, everybody. This is related rates for Cal 1. Okay. So before we left for our double spring break, we learned implicit differentiation. So related rates, we'll use implicit differentiation. But this time we will implicitly derive with respect to time. So X and Y are going to be certain quantities, and they are going to be differentiated with respect to time t. So when we solve related rates problems, some steps are to always draw a diagram, determine what quantities we are using, create an equation for these quantities, find out what equations we need, and then after we find our equations, we will take the derivative with respect to time, the implicit derivative, and then we will plug in values for our variables. We never want to plug in anything in the beginning unless we really, really have to. Okay, so notations down here. So here we are taking the implicit derivative with respect to time, d over dt. So in the book, in your homework, possibly the notations will be noted as d over dt of x is dx over dt, or as we like to keep it simple, x prime. Same with y, d over dt of y equals dy over dt, or keep it in simple again, y prime. So this is the key we want to reference. So just know that they're the same. dx over dt, the same as x prime, okay? Okay, so let's try this out. Okay, number one. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so for this one, we need to know the volume of a sphere because we want to know how fast is the volume increasing. So it says volume increases. Okay, and let's see. Well, it's giving us a volume that's increasing. So we want to know how fast is the radius increasing as the volume increases. Okay, so I'm going to label the things that we are given. Okay, so that being said, keywords here as well is increases or rate. Remember, we are doing derivatives, so derivative means rate of change or rate of increase or decrease. So look for those keywords to determine what variables you need to use. Okay, let's see, so reading it again, volume increases at a rate of 100 centimeters cubed per second. So this means that, let me bring this down a bit so I can get closer. So this means that V, they're giving us V prime already because it says the volume increases at a rate. So V prime is 100 cubic centimeters per second. And then what we are looking for is, what color is it? I'll change the color. Let me see. There you go. And then it says, how fast is the radius of the balloon increasing? So how fast is the radius of the balloon increasing? So this means that we are looking for R prime. We're looking for R prime. Okay. With that being said, the last clue given here is that the diameter is 50 centimeters. Well, if the diameter is 50 centimeters, this means that the radius must be 25 centimeters. Okay, so this is all the information given, which means, again, we want to take the implicit derivative first before plugging in any values. So that's what we're going to do next. So I'm going to say d over dt of v equal to d over dt of 4/3 pi r cubed. Okay, which means that d over dt of v, well, that's just going to give me v prime, equal to 4/3 pi. Now, the only thing we're taking the derivative of on the right side is the variable. 4/3 pi is a constant, so we can just move that to the outside. So this means that we only want the derivative of r cubed, the implicit derivative of r cubed with respect to time. So this is going to become 3r squared r prime. Okay, now let's clean it up. And I get v prime equal to, of course, this 3, that 3, cancel. You are left with 4 pi r squared r prime. Okay, and now we are looking for r prime. So we want to know how fast is the radius of the balloon increasing. So to solve for r prime, we're just going to divide by 4 pi r squared. 4 pi r squared. Okay. And what we now have is that, oops, v prime over 4 pi r squared is equal to r prime. Okay, now we've taken the derivative implicitly. Now let's check our formula and see if we have everything we need. Do we have a v prime? Yes, that's the 100 cubic centimeters per second. Do we have an r? Yes, that's the 25 centimeters. Since we have those components, now we plug them in after we've taken the derivative. Okay, so how much room do I have on here? Whoops. I got tons of room, so I'll just plug them in. Okay, so I have 100 cubic centimeters per second over 4 pi parentheses 25 centimeters squared. And then this is going to become 100 centimeters cubed per second over 4 pi times 625 centimeters squared. Type this in your calculator. Let me see, fraction. And when you type this in, you should get 0.0127. That's perfect. Centimeters per second. The reason centimeters per second is because my cubic centimeters cancels with my square centimeters. And there we go. I mean, we could even round this to 0.013 centimeters per second. So what this means is that if the sphere is, the volume is increasing by 100 centimeters cubed per second, this also means that the radius must be increasing by 0.0127 centimeters per second. So two things depend on time. Volume increases, radius increases. And we could even do surface area if we wanted. So volume, the surface area of the balloon also expands too. So this is why we use related rates. Two things depend on each other, and these two things are dependent on time. Okay, next. Okay. 2, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, like I said, diagram. Always draw a picture. Why not? Draw a picture. Okay, so here my ladder rests against the vertical wall, and guess what shape that makes? Okay, so we're gonna have our triangle, somewhat of a triangle. Okay, so my ladder is 10 feet long, so this will be 10 feet. And then the bottom of the ladder slides away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So here, this is 6 feet. Okay. Great. Now I would say complete your triangle just to get enough information. So again, you can use Pythagorean Theorem. A squared plus B squared equals C squared, right? So we can label that a step. We can say find height. And that would be 6 squared plus B squared equal to 10 squared. So 36 plus B squared equals 100. Then B squared equals 64, and B would be 8. So there's the height of the wall, right? Find height. So this would be 8 feet. Okay, so now we found that. But now, the other piece of information given is that the ladder slides away from the wall at a rate of 1 foot per second. 1 foot per second. So this ladder is sliding away from the wall at 1 foot per second. So this means that we are sliding up this way. Let me move this. And we're going to put 1 foot per second. That's our ladder sliding up that way. And what we want to know is how fast is the top of the ladder sliding down. So when the bottom of the ladder is 6 feet from the wall. So we want to know is how fast is the ladder going to fall down. Okay, so we have our right triangle. We've labeled everything. Now we need to know what formula could we use to represent this ladder falling. And we have to base our formula on kind of the shape that we created. Well, there's 2 formulas for a triangle, and one would be area, but we're not looking for area. Here, we want to know just how fast is the top of the ladder falling down. So the easiest formula to use here would be the Pythagorean theorem. So if I make that a step, let me bring this down. We can say find, let's say, find, and we're using A and B. So let's see, if I said A was the base and B was the height, I guess I should label everything nicely. So this is A, this is B, and hypotenuse is always C, right? So if we know that B is 8, and if B is falling, if the top of the ladder is falling, then this means we're not looking for B, we're looking for B prime. Looking for B prime. B prime will represent the top of the ladder. Okay, so the formula we use is going to be A squared plus B squared equal to C squared. We're going to use the Pythagorean theorem to solve this. Okay. And now, let's take the implicit derivative with respect to time. So we'll say d over dt of a squared plus b squared equal to d over dt of c squared. Okay, so we are taking the implicit derivative with respect to time on all three of these variables. So we end up with is 2a prime plus 2b prime equal to 2c prime. Okay. So we know a value for A, we know a value for B, we know what A prime is. Let's go back and look at the triangle. If you don't know what A prime is, since A is the base of our triangle, and A represents that the ladder is 6 feet from the wall, and if the ladder is sliding out, this means that A prime must be 1 foot per second because the ladder is sliding away from the wall at 1 foot per second. So over here, I'll write that for you. A prime is 1 foot per second. And when the ladder falling down, which is what we're looking for, B prime represents the rate at which the ladder is falling. Okay, perfect. Which brings me to, what would I say, a point. So the ladder, which is represented by C, the ladder is 10 feet, which means, is there a need for C prime? And if you don't know, then C prime would represent the ladder changing its height. Well, if this 10-foot ladder is falling, when it hits the ground, it's still going to be 10 feet. So this means that since the ladder is falling, it remains a constant 10 feet. This means that C prime must be 0. C prime has to be 0, and the only reason C prime is 0 is because the ladder remains a constant 10 feet. No matter how the ladder falls, where the ladder falls, it's still going to be 10 feet. And C prime, remember the derivative, represents a rate of change. Well, nothing's changing. No matter where that ladder falls, it's still 10 feet. So this means that C prime has to be 0. Okay, so we can put that in there. Let me see. Can I come here? Go over here, yes. Okay, because we're almost there. And then, let me see. So C prime is 0, only because the ladder remains a constant 10 feet, no matter how it falls. Okay, so Let's come back to the equation and plug in what we know. And sure, you could divide everything by 2, but let's keep going. Let's plug in, we know A, we know A prime, we know B, the only thing we don't know is B prime. So we can plug in and solve from there. So I get 2 times 6, and I'll put my units in, feet, times A prime, which is 1 foot per second, plus 2 times 8 feet times B prime, the thing we don't know yet, equal to, well, if C prime is 0, the whole right side is 0. Okay, let's keep going. On the left side, I get 12 square feet per second, plus 16 feet times B prime, equal to 0. Now we want to solve for B prime. Move 12 over to the right side. And I get, bring this down a bit. I get 16 feet times B prime equal to negative 12 square feet per second. Now, all we have to do to solve for B prime is divide by 16 feet. Maybe I keep these in parentheses the whole way in case my T looks like a plus sign. Okay, all right. Divide by 16 feet. Come on. There we go. Divide by 16 feet. Divide by 16 feet. My units of feet will reduce. That 2's gone. Those feet are gone. And then what we are left with is B prime is going to be a negative 12 over 16 or a negative 3/4 feet. 3 feet per second. And yes, don't be afraid to change these into decimal numbers. So this can be just negative 0.75 feet per second. So what this means, of course, we always want to know what this means at the very end. Not doing that. Is that, well, as this ladder slides out to the left and starts falling down, or slides up to the right, doesn't matter how it slides out, right? As this ladder slides out, we know the top of the ladder is falling down. So we want to know how fast, at what rate is this ladder going to hit the ground at? And this ladder is going to hit the ground at, it's going to fall at a rate of 0.75 feet per second. All right? And if you're wondering why the answer was negative, is because if the ladder is falling, you can see that as a rate of decrease. You're falling. So this is why our answer is negative. If we wanted to state our answer from English to algebra, oh no, sorry, from algebra to English, we would say the ladder is falling at a rate of 0.75 feet per second. There you go. Okay, so again, label everything we have, draw a diagram, don't plug anything in, find out what formulas we should use. So that's what we have to do. So once you piece everything together, we have to wonder, what formula are we going to use? Okay. All right. There we go. Here's a good one. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. And for this one, of course, on my notes, I help you out all the time. This one, you're going to need to know the formula for the volume of a cone. Because here, we want to know what rate is the water level rising, so how's the volume filling up, right? Okay, so first off, diagram. A water tank has the shape of an inverted circular cone with base radius 2 meters and a height of 4 meters. So let's see how pretty I can draw my diagram. Good enough. I can make that straighter. There we go. And this, I can make it dashed. Dash, dash, dash. This will represent my radius of 2 meters. And then dash, dash, dash. That'll be my 4 meters. So if I put some colors on here, 2 meters, this is 4 meters. Okay, so this diagram represents the inverted circular cone that has a base radius of 2 meters and a height of 4 meters. Now, water is being pumped into the tank at a rate of 2 meters cubed per minute. Find the rate at which the water level is rising. So let's just stop and read those again. Water is being pumped into the tank at a rate of 2 meters cubed per minute. Would that be the rate for volume, or would that be the rate for height, which is represented by h in the volume of the cone? That is going to represent our volume, the rate of volume. So if water is being pumped into the tank at a rate of 2 meters cubed per minute, this means that the volume is increasing at 2 meters cubed per minute. So let me see, over here, I think I'll label what they're giving us. So they're saying that V prime is 2 meters cubed per minute, because that's how fast the volume's filling up. Okay, and then let's see, find the rate at which the water level is rising when the water is 3 meters deep. So now, here it is right here. Find the rate at which the water level is rising. Guess what variable represents all of that? So we want to know the rate at which the water level is rising. So this means that height is changing, height is rising. So this means we are looking for h prime. We're looking for h prime. So I'm going to put down here h prime. That's what we're looking for. Okay, and the very last part of the paragraph or problem says, when the water is 3 meters deep. Well, I'm going to draw that on my diagram. This is a little tricky problem, but I don't want to label R, I don't want to label H just yet. Let's go ahead and do my diagram. So coming back to my cone, we said the water's 3 meters deep inside the cone. Okay, so that means over here, let me change the color of my water. There we go. All right, so that's 4 meters. I'm just gonna say, here's my water level, okay? So there's my water level. And out here, we know that this is 3 meters. Okay, so I just want to draw that in my diagram. Okay, all right. So now, with that being said, we have our diagram. We know what formula we are using, which means that we can now take the implicit derivative, okay? We're going to take the implicit derivative, but there is a word of caution on this, okay? There is a word of caution, and I'll show you in a second. I'm going to write it down. So over here, let me do this. I'm going to say take derivative, right? Yeah, we'll just do that. So I'm going to say take, oh, this might make it simple. I'm just going to say take d over dt of volume. Not being friendly today. Okay, so this means we have d over dt of v equal d over dt of 1/3 pi r squared h. Okay, so left side simple. Left side becomes v prime. Right side, just like with the last problem, or no, the very first problem, 1/3 pi is our constants, so we can keep those out. 1/3 pi, right? Times. Now, I'm going to take a break here because we are implicitly deriving, and all we want is the derivative of r squared h. Well, r is its own function, h is its own function. And when you have the product of two functions, we are going to need the product rule on this. Okay, so I'm going to walk you through this, but again, there is something I want you to look for. This is my word of caution. So let's product rule this. This means that f would be r squared and g would be h. And these are implicit derivatives. So f prime would be 2r r prime. G prime would be h prime. If we put it together, f prime g times g prime h, we get 2r r prime h plus r squared h prime. Now here is what I said to look out for. Okay, so we know a value for r. R is 2 meters, right? But that is if the tank fills up. So that's why I said I don't want to plug anything in just yet. But R is fine. Height, well, we know we want to know what is the rate of the height increase when the water is 3 meters deep. So we can assume that height will be 3 meters. Okay. Then r squared, we know r could be 2, h prime is what we're solving for. So what I'm getting at is the only variable I did not say. The one variable I did not say was r prime. Here's where it causes an issue. Our cylinder, our cone, is the radius is 2 meters. So as the water rises, no matter what, the radius is still going to be 2 meters. So we're not looking for an increase in radius because no matter what, the radius is 2 meters. So it's not increasing anywhere. Sure, from the bottom of the cone to the top of the cone, the radius is probably different. But as the height is rising, the radius is going to be, if the cylinder fills up, the radius is still 2 meters no matter what. So there is no need to have an R prime. We do not need an R prime, which means that we have to come back to our cylinder and make a geometric substitution for R. We have to get rid of R, because if we don't get rid of R and we still try to take the derivative, we're going to end up with an R prime, and we have no idea what R prime is. I'm sure we could solve for it if we had time, but there's no need for it. So let's make our lives easier and make a substitution for R to get rid of this R prime. So we don't need any of this. So I can even write that down. I can take note. And R prime, we don't need. Say, don't need. And we also don't know. And is that a saying? What you don't need is what you don't know? Or what you don't know is what you don't need? Probably not. But you get it. Okay. Which means now, since we don't need it, we don't know it, we need to make a substitution for R. So with that being said, I'm going to draw an arrow. Let me see. I'll just come back over here. I'm going to say, let me bring this down. Make a sub. This does not want to work for me today. Make a sub for R. And the word I said probably like 2 minutes ago was geometric. And the reason I say geometric is because if you look at our cylinder, well, whatever I drew and saw when I drew the radius and the height inside the cylinder, it makes a specific type of triangle. It makes a right triangle. So that's where we're going to start first. We are going to draw the right triangle of 2 meters and 4 meters inside my cylinder. So that's our next step. Okay. So there we go. So this is 2. Work for me today, work for me. This is 2, and this is 4. And now, inside our cylinder, well, we actually have another right triangle, which is represented by the height of the water. The height of the water is 3 meters. So let's make a triangle for that. And I'll change color on that. Wait, doesn't. There we go. Okay. So this makes our triangle. We know that it's 3, but we don't know the radius. So again, let's avoid trying to plug any numbers in. So when the water's at a height of 3 meters, we don't know the value of the radius when the water's at 3 meters. So we're going to label it R. Yes, we know the height is 3 meters, but again, we don't want to plug anything in. So for height, we're just going to label it as H. And now, when we make the substitution for R, we are going to do it by similar triangles. This is how we make our substitution, by the use of similar triangles, which means that you can set their proportions equal to each other. So when I do this, we know that 2m is equal to R. So 2 meters is equal to R because we are comparing the proportions. So the base of the triangle on the left is going to be equivalent to the base of the triangle on the right. So 2 meters equals r. And then I said proportions. So now the height, 4 meters, is going to be equal to our height of h. Now we're making a substitution for r. And one thing you can do already, cross out those units. Well, all we have to do to solve for r is multiply h to the left side. And you can also reduce this as well. 2/4, 1/2. Okay. And then I'll multiply the h over. And this means that I'm going to get, my goodness, work for me today, work. I'm going to get h over 2 equal to r. And this is our sub. Okay, so with that being said, let's come back up to taking the derivative of volume. Okay, so now I'm going to get rid of this step. Let's see. I'm going to get rid of this. Okay. And now, yes, the left side becomes v prime. So we can start there. I can say v prime. And then, again, I'm going to take the constants out. 1/3 pi times d over dt. So I'm not taking the derivative of the right side just yet, because now I'm going to plug in our substitution for r. Times my new r value of h over 2. So, and since r is being squared, this has to be h over 2 squared times h. And again, I just took this h over 2 and I plugged it in for r. There you go. Plugged it in for r. So that's all that happened. Okay, so let's keep going. This is still v prime equals 1/3 pi. And not ready to take the derivative just yet. We still have some cleanup to do. D over dt of now h squared over 4 times h, still going, 1/3 pi. Actually, I can take out the 1/4. So 1/3 times that 1/4 is now going to give me 1 over 12 pi d over dt of h squared times h, which gives me h cubed. Okay, now we are ready for the derivative on the right side. Implicit derivative at that. So I get v prime equals 1/12 pi times the implicit derivative of h cubed, 3h squared h prime. And now we get what we want. So we were looking for h prime in the very beginning. That's what we had set up for, but we had to do some substitutions because we were getting stuff that we didn't need it, such as that r prime. So now we are at the stage where we can solve for h prime, which is what we want. Now let's rearrange this whole thing for h prime. So first, cleanup. This 3 becomes 1, and this 12 becomes 4, because we're multiplying together, and 1/12 times 3 is 1/4. So now my rewrite, v prime equals 1/4 pi times h squared h prime. Okay, now again, we're solving for h prime. Don't forget that. Solving for H prime. So isolate H prime to one side, which means we need to get rid of the 1/4, we need to get rid of the pi, and we need to get rid of the H squared. Okay. So to do that, let's see. Okay, well, to get rid of the 1/4, I'd multiply both sides by 4. So 4v prime equal to pi h squared h prime. And then I would divide by pi h squared. So now you would have 4v prime over pi h squared equal to h prime. Now we have isolated, we have solved for h prime. Now we plug in what we know. We know that v prime is 2 meters cubed per minute. The other thing we need is h. We know that h is 3. Now, I know you've been waiting for it. You get to plug in 3 for h. And the reason we plug in 3 and not 4 is because we want to know what is the height increasing at when the water is 3 meters deep. 4 represents the height of the cone, but the water is at 3 inside the cone. So we plug in 3 instead of 4. Okay, so 2 meters cubed and 3 meters. All right. So 4 times 2 meters cubed per minute, right? Was that minute? Yes, minute. Two meters cubed per minute over pi times 3 meters squared equal to 8 meters cubed per minute over pi times 9 meters squared. And let's cancel some stuff out. Meters squared, meters cubed. And now the rest we type in our calculators. So let me see. 8 over just 9 pi, right? 8 over 9 pi, yes. So I get 0.283 meters per minute. Okay. So again, what it means is that our cylinder, or our cone, I keep saying cylinder, our cone is filling up. But right now, since the cone is 4 meters high, the water's at 3 meters. And we want to know how fast is the water rising when it's at 3 meters. And when the water is at 3 meters, it is rising at 0.283 meters per minute. And there you go. That's it. Okay, and let's just go over this again. Am I drawing on it? I just did, my bad. Let's go over this again. Okay, just recap really fast. Oh, that looks fun, all those edits. Okay, so we drew our diagram, we labeled pieces. We knew R was 2 and the height was 4, but those represented the actual cone. We wanted, my dog just got bored. He doesn't like calculus. He left. Okay, so now we know that the height of the water in the cone was 3 meters high. And since we labeled everything, we thought we had all our components, we could take the implicit derivative. But when we took the implicit derivative, we came out with a variable we didn't need, and that variable was our prime. Because all we wanted to know is how fast the height of the water is increasing. We don't want to know how fast the radius is increasing, because that really doesn't matter, because since we're inside this cone, if the height is rising, then if the cone fills up, the radius is going to be 2 meters. So we don't really care about the radius increasing. So with that being said, we needed to get rid of that r prime. And the way to do that was to make a substitution for r. And the way we did that was by the use of similar triangles, or we could call it a geometric substitution. Okay, and that's what we did. We know that when I drew the diagram, you could see there was a right triangle inside my cone, and the water at 3 meters also created another right triangle inside the cones. So we made a substitution by the use of similar triangles. 2 over 4 equal to r over h. And we could rearrange that equation in terms of r. So I made it r equals h over 2. Plug that in for r. Then the whole equation on the right side was in terms of h, which means we could take the implicit derivative, simplify, 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 rearrange for h prime, and plug in the numbers that we know. That's it. That's it. Okay. Awesome. All right. Let's keep moving. All right. Cool. All right. 4, car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the 2 roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, again, always, always, always diagram. Let's have fun with this one though. All right, so car A is traveling west, that way. That way, that way, that way. And car A is traveling north. Okay, so car A is traveling west. So we're gonna make this car A, and we're traveling west. Ooh, look at those fun colors. Okay, so this is car A. Guess I should label that, huh? So this represents car A. And to make it better, there you go. Car A is traveling west at 50 miles per hour. Okay, we'll label stuff later in a second, like really quick. Then car B is traveling north, and they both are headed for the intersection of 2 roads. So we assume they're both approaching the same intersection. So here's going to be car B. Yeah, still use that. So car B is approaching the intersection. So here's car B. Okay. Well, guess what? If I connect the 2 ends here, we make what type of triangle? A right triangle. I mean, mine sure. Maybe looks like a right triangle. Okay. And also, what could be noted is that the length I just drew represents the distance from car A to car B. Okay, so that's going to be important. So keep that in mind. All right, so now let's label some stuff. And we said that car A is traveling west at 50 miles per hour, which means that that's not A, that is A prime, because 50 miles per hour happens to be a rate. That is a rate. So right above A, I'm going to say A prime, 50 miles per hour. But if we look at the very bottom of our problem, it says car A is 0.3 miles from the intersection. So that gives us a value here. 0.3 miles. Okay. And then let's look at car B. Car B is traveling north at 60 miles per hour. So that's not B. Again, that's B prime, because remember, our primes represent our rates. So this means that B prime, nope, don't do that. Stop it. I can just do it here. Let me see. There we go. B prime is what, 60? And then over here, I'll just rewrite this. B is 0.4 miles from the intersection. Okay, well, at this point in time, if you want to know how far each car is from each other, guess what special theorem you can use for a right triangle? Pythagorean theorem again. Or you could just recognize that this is a 3, 4, 5 special triangle. So this means that what we're going to call length C is going to be 0.5 miles. And you can do it by Pythagorean theorem just to prove it. And now, let's actually figure out what we're looking for. We want to know at what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection. So we want to know at what rate are they approaching each other, which means that we're looking for the rate at which their distance is decreasing, right? So if C represents the distance from car A to car B, which right now they are 0.5 miles away from each other, this means to represent the rate of change in their distance, we are going to represent that by, guess what? C prime. C prime. Okay, so our job is to look for C prime, and since this is a right triangle, we can use Pythagorean theorem to solve for C prime. So let's do that. So over here, I'm going to say, let me change up colors a bit. Let's say solve for C prime. Okay, using Pythagorean theorem. A squared plus B squared equals C squared. Now we know we have everything labeled. We know the formula we're using. We don't plug anything in. We are now ready to take the implicit derivative with respect to time. So d over dt of a squared plus b squared equal to d over dt of c squared. And over here, left side, 2a prime plus 2b b prime equal to 2c c prime. Okay, and we're looking for c prime. But before you do so, if you notice it, you can divide everything by 2. So let's do that. A prime plus b prime equal to c prime. And the reason I'm writing c prime is because when I divided everything by 2, I could also divide everything by c, like C, senor. So with that being said, I'm going to make this all over C. Okay. All right, well, you know A prime, you know B prime, and you know C. Plug them all in. So let's see. What was it? A was 0.3. So yeah, there we go. A is 0.3 miles times. Okay, so here I'm going to change something up on you. So these two cars are approaching the intersection, which means if you're a normal human being, you should be slowing down, which means your speed should be decreasing. So all I'm going to do here is take our miles per hour and make them negative, because if they're both approaching an intersection, their speed should be decreasing. You should be hitting the brakes, okay? So negative 50 miles per hour plus 0.4 miles times negative 60 miles per hour, all over 0.5 miles. And plug it in your calculator, type away, and let's see what we get. Division 0.3 times negative 50 plus 0.4 times negative 60 all over 0.5. 78. Okay. So we get negative 78 miles per hour. Okay. And again, the reason I made them negatives is I'm assuming that we're normal human beings and don't like to run red lights in this fantasy world. So when you are approaching the intersection, your speed should be decreasing. That's why it's negative 50 and negative 60. Because if you're approaching, two cars are approaching each other, then their distance is decreasing. I guess that's the better one, right? The mathematical explanation is that your distance, if you're approaching each other, your distance is decreasing. And since we're decreasing, this is why my rate is negative 78 miles per hour. There you go. So one real world fantasy situation and one mathematical explanation put together. There you go. Okay, last one. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the, there we go. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay. Oh, well, who cares, right? Well, we do, so let's solve it. Okay, diagram first. A man walks along a straight path of 4 feet per second. So let's draw that out. So he's walking a straight path, somewhat straight, right? Of 4 feet per second. Okay, so maybe we could draw that in. So our guy is walking at 4 feet per second. Somebody convert that to miles per hour. We don't walk in feet per second. We walk in miles per hour, even though we have feet, but we don't understand. Okay. Okay. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. So it's located on the ground 20 feet from the path. So when we're doing related rates, we have to assume a lot of stuff in our diagrams. So we're going to assume that the path started here and our searchlight is located on the ground 20 feet from the path. So there's my searchlight, okay? All right. And we know that this is 20 feet. Okay. Well, guess what? If you connect these two, you have another type of triangle. We get another right triangle. Okay. So with that being said, one more thing to put on is that at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So this guy is walking, and he's walking at a rate of 4 feet per second, but he's already gone 15 feet. So this pathway that he's walked is also, I'll put that there, he's also walked 15 feet. So this pathway is 15, or I can even put it down here. He's walked 15 feet so far. And then here, down here, I'm gonna put my searchlight. So I'll do that. And we're keeping an eye on this sketchy dude walking at this strange rate of 4 feet per second. So there is my searchlight on this fellow. And it is rotating, right? So the searchlight rotates, which means that, let's read the problem again. Well, just the second part of the problem. What rate is this searchlight rotating at when the man is 15 feet? So if our searchlight is rotating, this means we're looking for the rate of change in an angle, right? We're looking for the rate of change of an angle. If we're rotating, then it rotates at a certain angle, right? And that angle has a rate of change if it moves back and forth. So down here, we're gonna put theta. Does it look like a theta? I'm trying my best. Whatever, there's theta. Okay, so our spotlight is rotating back and forth, right? It followed this sketchy dude, and we wanna know what's he up to, but we also wanna know what rate is our angle rotating at. Okay. All right. So again, this is a right triangle. So first thing we can do is find all three sides. 20 feet is the height, 15 is the base. Using Pythagorean Theorem, what's that? 400 plus 225, that is 625. So the distance from spotlight to man right now is 25 feet. I hope. I just did that in my brain, okay? 25 feet. Oh, sorry for all this random fonts. My bad. That one's a little bigger than I wanted. It's okay. That's 25 feet. Okay. So, but now, this is a right triangle, but this is going to be different from the other two problems that had right triangles because we're not looking, I mean, we could, because if he keeps walking, then yes, his distance is going to change. But right now, this sketchy dude has walked 15 feet and has stopped. So right now we know that the distance from the spotlight to the guy is 25 feet. And he stopped there doing something. Who knows? Okay. So what we really want to know is what rate is our angle changing as this searchlight is rotating. Okay. So with that being said, if we're looking at an angle, we need a trig function that could represent the rotation. Okay. So from our angle, let's see, we have to figure out what function could represent. So we can start first with sine. Sine, let's see, I'll just write this down, right? If we try sine out, if I say sine of theta, remember sine puts opposite over hypotenuse. So sine puts 4 over 25, right? That puts 4 over 25, which doesn't really, sine function doesn't really cover what we need it to do, right? Or even better, remember I said don't plug in values because that's wrong. So here, before I even get started, this is going to be, the base is going to be x. So the base is going to be x, and the height is going to be y. Why not? Okay, so sine would put x over my hypotenuse of 25, which we'll say z. So x over z. But we don't want to use the sine function because the sine function doesn't cover the whole rotation. It only puts the opposite side over the hypotenuse. So that's the only area it would cover. So that's not going to work out. So that doesn't cover it. We can try cosine. Cosine theta. Okay. Well, cosine theta, cosine would put the adjacent side 20, so it would put y over z. Okay, that would put y over z. Okay, so there are other reasons of why we're not going to pick these trig functions, which I can get into a little later. So with that being said, cosine does y over z. So you think that would cover the area because we go to y and we go to z. But now, the reason this isn't going to work is because now, let's say I take the derivative, the implicit derivative. If I decide to take the implicit derivative of y, I'm going to get y prime. Now, what we see here is that y represents the pathway, which is 20 feet. Is there a reason to have a y prime? No, because no matter what, the pathway is still going to be 20 feet. So the pathway is not changing, which means no matter what, it stays 20 feet. Since there is no change, y prime would be 0, and that would give us nothing. It would zero out the whole equation. So none of this is going to work either. Okay? All right. So let me just erase all this. So we can come down to one more function, which actually might work. Let's try out tangent of theta. All right, tangent theta. Well, tangent puts opposite over adjacent. Opposite over adjacent. Well, that looks like it covers the whole area. Because you do opposite over adjacent, it covers the base of the triangle, and it covers the height of the triangle. So tangent would put x over y. Tangent would put x over y. Okay. So yes, I mentioned earlier that we don't want to use y because we'll get y prime, which means now it is probably okay to take the derivative and plug in for y beforehand. Okay. So a lot about, I can cover them at the very end of why we didn't choose sine and cosine again. Tangent is going to be our best bet. Okay, so with that being said, we can take the implicit derivative, but I'm going to multiply y to the left side first. This will make the derivative easier, so we don't have to do a quotient rule on the right side. So I'm going to rewrite this. Y times the tangent of theta equal to x. Okay, well, I'm kind of backtracking because I already said we can plug in for y. So let's go ahead and do that. So y is 20 times tangent theta equal to x. So it's still good that I multiplied y to the left side. Either way is fine. Okay, so now let's take the implicit derivative with respect to time. So d over dt of 20 tangent theta equal to d over dt of x. Okay, so on the left side, 20 is a constant, So 20 will stay outside. Now remember the derivative of tangent. The derivative of tangent is secant theta. But we're also taking the implicit derivative of tangent, which means we also need the derivative of theta on the inside. So this also includes a chain rule. So this means this will not just be 20 secant theta. This is going to be 20 secant theta, theta prime, equal to x prime. Now let's take a look back. We want to solve for the rate at which the angle is changing, which means we are looking for theta prime. So I could have wrote that. We didn't label everything on this one. See, I'll get used to this when I start recording more videos. But here it is. So, oh goodness, there we go. Theta prime is what we were looking for the whole time, because that represents the rate of change of the whole problem. Okay, and there were some things we knew already. We knew that x was 15 feet. We knew that y was 20 feet. And we also knew that x prime was 4 feet per second. So this is the stuff that we knew. Okay. Now, we have everything labeled. We've taken the derivative, and now our job is to solve for theta prime. Which means I can divide by 20 secant theta. So maybe I didn't have to move the 20 over there at all. Oh well. So divide by 20 secant theta, which means I'll have theta prime equal to x prime over 20 secant theta. But now, remember, secant is 1 over cosine. So I can rewrite this as x prime times cosine theta over 20. Okay. Well, now, let me see. Yes, we did that. And yes, we know that. Okay, perfect. Okay, just making sure we're on track. Well, we know the value for x prime. X prime is 4 feet per second. We know the value for y, which is 20 feet, which is already there. And now we need to know what is the value for cosine theta. Well, we just go back and reference our triangle. And cosine is adjacent over hypotenuse. So the cosine of theta, I'll write this down here. Cosine of theta is actually equal to 20 over 25. And if I put the units of feet, well, they would just cancel. So cosine is actually 20 over 25, or divide by what? 5, you get 4/5. Okay, so that's what we'll plug in. So here we go. We now know everything to plug in. So I get theta prime equals, parentheses, 4 feet per second times 4/5 over 20 feet. Now let's type that in our calculators. There we go. And of course, when typing this in, your units of feet would cancel. And what we end up with is 16 over 5 or 16 over 100, which gives me 0.16. And now remember that since we're solving for theta prime, in calculus, all of our angles must be in radians, and we're looking for a rate of rotation. So my answer is going to be 0.16 radians per second. That is how fast that is the rate that our flashlight is rotating at. Okay, or searchlight. Okay, so little edits here of why we didn't choose everything else, right? Why cosine and sine didn't work. So let's see. If I do this down here, let me separate that. Let's see. Y over z, which means that you'd get a y prime, you'd get a z prime, which we don't want, which means that you would plug in, and that would be 20 over 25. And if you take the derivative, that would be equal to 0, which means theta would be equal to 0, which gives us nothing. Okay. Now let's try it out with sine. So sine theta would have been x over z. So that's my bad. Okay. And then since z is not going to change, we can make this x over 25. Take the derivative. You would get cosine theta. That'd be negative, but whatever, over there. So this would be cosine theta, theta prime equals x prime over 25. And then this would be theta prime equals x prime over 25 times cosine theta. Plug in our numbers. 4 feet per second over 25 times cosine theta, which we found to be 20 over 25. So 4 over 5. So this would be 4 over 5. And then typing that in, you would end up with 4, that's feet there, so those would cancel. You would have 4 radians per second over, and that 5, and that would become 1. That would become a 5, and that'd be 20. 4 over 20, and this would be 1/5 radians per second, which is again what we don't want, because sine does the opposite over the hypotenuse. So opposite over the hypotenuse does not cover the whole range of the actual theta. And I'll write that in your notes for you. It does not cover the range of the whole theta. Okay. Now that is it for related rates. Sorry for that mistake on the last one, or on this little bottom part, but that's it. Okay, see y'all later.